Okay, welcome to bonus coverage. You made it. Right. You will not be disappointed. I promise you will not be disappointed. Hey, check it out. Here is a function f a to b, blue area, right? The definite integral would be able to find that, but here's the problem. We only know how to approximate that area, right? We can use a Riemann sum, but how do we get the exact area? I'm sick of approximating. I want the exact area. Well, first thing we got to realize is, hey, look, that interval A to B, we need to chop that sucker up into as many subintervals as we possibly can. Because the smaller those little rectangles are, the closer they fit to the actual curve. And all the little parts that we're missing or the parts that are too much, right? They're going to be, that's going to disappear if those get infinitely tiny. So how do we get them to be infinitely tiny? Each one of these subintervals needs to be infinitely tiny. Each one of those subintervals, we can say each one of those is a delta x wide. Well, what's the width of each one of them? We want to take the total interval size, which would be b minus a, and we want to divide that total interval size by the number of rectangles we want, or subintervals that we want in this interval, which would be n, right? We want n, and eventually we're going to make n go to infinity. Hold off on that. So what we want to do now is on one of these subintervals, right? We want to select any x value that exists on a subinterval, right? So we're going to call that point C sub I. So C sub I, that's just any x value on the ith subinterval, right? So pick a subinterval, there is going to be a C value that we're going to use to get the height of a rectangle. So C is just going to be somewhere in there that we'll use to get a height. So we'll apply the function to that C value, get ourselves a rectangle, and then we're going to do that an infinite number of times. So C sub I, we're going to define it. And if you haven't read the article that I posted, I actually wrote it. I know it's so brilliant. But that one, hopefully you're here because you read through that and you wanted some commentary on it. So C sub I, we're going to select C sub I, not as just any random point, right? It could be any x value on the interval. It's hard to actually work with a random point. We want a point that we know. And boils down to it, and we use the right endpoints. We could use the midpoints. We could use the left endpoints. It wouldn't matter. Like the calculus, the math, the limits, the summation, it's all going to work out. But the right endpoints are the easiest endpoints to work with. Here's why, right? So we are going to take a look at a really zoomed in version of the interval from A to B. In fact, it's so zoomed in that these infinitesimally small subintervals are now that long. We're going to call A x sub 0. This next little break is x sub 1. This next little break is x sub 2. All right, so C sub I could actually be anything in between, any x value on the interval a to x sub 1. So I said the right endpoint, that one right there, is the easiest one because the first right endpoint is a plus boop, a single jump in x. So a plus delta x. The second right endpoint, which would be x sub 2, that one right there, well, that's boop, boop, that's 2 jumps away, right? So the second endpoint, or the second right endpoint, is a plus 2 delta x's. And the way it's going to work out, that the generic ith right endpoint, just any old ith right endpoint is going to be a plus I delta x. And that, friends, is what we want to use to define C sub I. So C sub I, that some point, some x value on the ith subinterval, we want to say is a plus I delta x's. Okay, so we got delta x, b minus a over n. We've got any old c value that's on any subinterval. Now we need to find the areas of some rectangles, right? So the area of a rectangle is the height times the width. So height times width. We know that the width, right? That the width is going to be represented by delta x. The height is a function value. So that is going to be the function value at an x value. Now I wonder what x value we're going to use. C sub I. We're going to use C sub I, right? The C sub I, just any of those values, any x value on the I subinterval. We're going to sub that into the function to get a height. We're going to multiply by the change in x. Now here's what we're going to do, right? We're going to add all of those areas together, starting from the first one. So starting from I is equal to 1. And we're going to stop at, which one? Oh, yeah, the last one. And how many did we use? Well, that was right. We used n subintervals. Okay, now what? Oh, what did we want to make n do, by the way? We wanted to make n go to infinity. And the only way to do that is with a limit. So we want the limit as n goes to infinity of the sum from I equals 1 to n of the product, get it, of f of C sub I times delta x. And that, ladies and gentlemen, is the limit definition of the definite integral from a to b of f of x dx. And that is a life-shattering moment. That's awesome. Check that out. That is some serious calculus going on there. Now, what's cool about it is that you can see some of the remnants of the definition in the notation of the definite integral. You see a height times a width, right? The height is f of x. You see the width is delta x, the width dx. The product of those two things is a definite integral. Man, it all comes around full circle, right? We're not changing anything. We're just learning it at a deeper level. We're seeing how things are connecting. I would love for you to stick around for a few more minutes while I do a definite integral by definition, just to prove that it can be done. Okay? If you're willing to stick with me, I'm gonna do one right now. Okay, so you can leave if you want to, if you don't want to see this. But I'm gonna, for those of you that are really bored, check this out. Okay, so I want to find the value. Do an easy one from 0 to 2 of 2x plus 3, the function. Okay, with respect to x. Now, as far as a picture is concerned, usually I like to draw pictures. Okay, so the picture of that would be a linear function, y-intercept of 3, slope of 2. There's the function f of x. And we're trying to find the signed area under the curve from 0 to 2. Okay, so that area right there, which some of you are like, wait, whoa. Why do we need calculus for that? That's a trapezoid. Come on, man. That is a trapezoid. I don't need calculus. Look, that's a trapezoid whose base is 2. That's 2. This distance is 3. This distance is the function value at 2, which is 7. And if I want to calculate the area under the curve 2x plus 3 from 0 to 2, all I need is geometry. And the area of that trapezoid is 1/2 of the base times the sum of the heights, 3 and 7. Well, that's going to be 10. Purvis, you don't need calculus for that. I beat you. I beat you. That's answer is 10. Get on my level. No, you get on mine, because I'm going to do that by definition. Look, the definite integral by definition says that the definite integral is the limit as n goes to infinity of the sum from I equals 1 to n of f of c sub I times delta x sub I. So we need delta x first. Delta x is b minus a over n. And according to this definite integral, we got 2 and 0. So delta x is 2 minus 0 over n. There's delta x. We gotcha. Now we need c sub I. C sub I is a plus I delta x. Well, the value of a is 0. Delta x is 2 over n. So now we know c sub I is 2i over n. So here are two little formulas we can now sub in. All right, let's keep this ball rolling. So we got the limit, n goes to infinity, the sum from I equals 1 to n, f of c sub I. And c sub I is 2i over n. So I'm going to sub that in. And delta x is 2 over n. Well, now, I'm going to keep rolling. What is f? F is the function 2x plus 3. So if I apply the function rule, so we're going to apply the function rule now to 2i over n. So that will be the limit as n goes to infinity, the sum from I equals 1 to n. F of the 2i over n is 2 times 2i over n plus 3. All of that multiplied by 2 over n. Now, all we've got this boiled down to is some summation properties. And there's all kinds of summation properties out there. I know we haven't talked about them, but we can still kind of work this out. So limit as n goes to infinity, the sum from I equals 1 to n. I'm going to try to multiply and distribute kind of all at once. So let me see. That's 4i over n plus 3. But I'm going to kill two birds with one stone and multiply by 2 over n as well. So I got 8i divided by n squared plus 6 over n. Now, summations I can break apart. So that's the limit as n goes to infinity. The sum from 1 to n of 8i over n squared plus the sum from 1 to n of 6 over n. Now, the way sums work is that if there's any like constant multipliers, we can factor those out, right? Because it's just the distributive property. So a constant is going to be things like 8 and 6, no doubt. But n is also a constant. N is also a constant because in the sum, in the summation, the thing that is changing, right? I'll highlight it. The thing that is changing is not n. The thing that is changing in the sum is I in this case. So I is starting at 1 and heading to n. So that means n is a constant. So any n's and any just numbers that I'm used to seeing, I can factor out. So that is still the limit as n goes to infinity. 8 over n squared times the sum from 1 to n of I plus 6 over n times the sum from, well, there's nothing left. Well, that means there's just a 1 left. Okay. So now we need to access some of the summation formulas. And there's all kinds of summation formulas out there. But if you remember the sum from 1 to n of I, the sum from 1 to n of I is, let me write it out for you. It is n times n plus 1 all over 2. You might remember that from adding arithmetic series together. Hopefully you do. Maybe it's first plus the last times the number of pairs. So the first 1, the last n, and then the number of pairs would be n over 2. That's where that comes from. So we're going to keep going. The sum of 1 from 1 to n, well, that's 1 n times. So what's the grand total? Yeah, it's just n. So that's multiplied by n. Now we're going to simplify a little bit. Hold on to your socks because we are almost there. We got the limit as n goes to infinity. I'm going to cancel a few things out, right? So the 8 and the 2, that's 4, the n there, and one of the n's down there. So let's see, we got 4 times n plus 1 over n. And then this simplifies to just 6. Okay, do you see it now? Do you see it? I see it. 6 and 4, 10. Okay, come on now. So the limit as n goes to infinity of this critter, right? We have a linear over a linear, right? The rules for limit at infinity, equal powers, just the ratio of the leading coefficients. That would be 4n over 1n, so that would go to 4. And the limit as n goes to infinity of a constant is the constant, 6. That's 10. That's 10, right? That's 10. Okay, we had 10 earlier, about 20 minutes ago, right? It's 10. Okay, so believe me when I say that the limit definition of a definite integral is amazing. It is awesome. I love all this stuff that we can do. There's going to be much simpler ways to calculate the values of definite integrals, but certainly it can be done with all of this pain and strife. So I'm saving you from a lot of this pain and strife. If you're interested in more of this, please let me know. I would definitely encourage you to keep thinking about this and pursue it, because there are some really awesome things that are coming down the road that will set the table for things like the fundamental theorem of calculus. So it won't be just something I just tell you or you look up online. It'll be something that you will feel like you've discovered on your own. And that is why math is so awesome, because you can recreate the thinking of people like Leonhard Euler and Bernard Riemann and Leibniz and Newton. Like, you can recreate their thought just by following the rules. It's awesome. Like, to know that we all have this capability. So thanks for joining me. I appreciate it. Stick with me. Now go check out the properties of definite integrals, right? This is just bonus coverage. So all you need to know is the properties of definite integrals and definite integral assigned area. So make sure you go watch those videos too. Thanks for being with me for a few minutes here. I know it's going to benefit. Hopefully I didn't confuse you. Oh man, dude, that was awesome. See ya.